Our next speaker is Dr. William Data Bryant, talking about predicting cyber attack likelihood using probabilistic attack trees. He is currently a technical fellow at Modern Technology Solutions Incorporated. He previously had a 25-year career in the United States Air Force, including serving as the Deputy Chief Information Security Officer. And before that, he also co-developed the Aircraft Cyber Combat Survivability, trying to provide a framework for understanding aircraft survivability during testing. Please welcome Data Bryant.
Do I just pick one of these? All right. Well, good afternoon. I have the coveted after lunch spot. So for those of you, some of you may know me, I typically go by Data. I have a number of roles. And so some of those roles are in support of DOT&E. You may have seen me in other contexts supporting a bunch of DOT&E projects. I'm here today in my role as a tech fellow that works for MTSI because this is all research that was done under IRAD and has no blessing from any government agencies or anything of that sort. So I'm going to talk about some of the research that we've been doing. Okay, so why are we even here? What's this all about? Many of you in this room probably know that we believe, in general, across the DoD, that our platforms and weapon systems are likely to come under cyber attack. That's why we're talking about cyber survivability. That's why we're worried about testing it. And so we need to figure out how well they will perform in a cyber contested environment. So one of the holy grails for that is the likelihood of a successful cyber attack. But that's also one of the most challenging things to measure. And there's a lot of debate back and forth as far as how to measure it or if it's even meaningful to measure it. What we're looking for is the equivalent of kinetic survivability's P sub H, or probability of hit. So probability of kill given hit is the step after that, which is your vulnerability versus survivability. Of course, I just said the V word. I hate using the word vulnerability, especially in what today will presumably be a mixed audience. How many of you would categorize yourself as survivability experts, or your primary interest is survivability? Okay, a few of those. And how many of you would categorize yourself as cybersecurity experts? And we've got a few of those too. So when you have a survivability person talking to a cybersecurity person and vice versa, and one of you says vulnerability, please know that the other person did not hear what you said, because that word means two distinctly different things in those two communities. And so anyway, I'll get off that soapbox. But you gave me some extra time, so I just used it. Okay, there is little relevant historical data. So if you think about it, if I want to talk about a hit to a fuel tank, I've got all kinds of testing and studies that have been done. I've got repeatable experiments, and I've got 80 years worth of combat data of airplanes blowing up or not blowing up when they get hit. I have none of that in cyber. There's very little consensus on how or even if to measure. So I'm going to show you an approach that we've worked out. I believe that probabilistic attack trees are scored using a combination of historical data where we've got it, simple models where we don't, and then direct assessment where I have to, provides a potential solution to figuring out a meaningful likelihood, which is all we're going for here. I'm not going for the right answer. I'm going for right enough to inform better decisions. Again, that's the final goal. Remember, we're building things. We're building airplanes, and we want those airplanes to be survivable enough to meet their mission objectives. Okay, so all of this is within the context of a thing we call URAMS. Somebody may have heard of it. It is often categorized as a mission-based cyber risk assessment. What it really is a big basket of tools. And so There's a very simple process of score, combine, decide, analyze, and within each of those is a set of tools. Now, I mention this because the tool I'm going to talk about, probabilistic attack trees, fits in here, and it's in response to real-world learning that we've had in executing these types of assessments on real-world systems. And so there's been a couple of sticking points, and these probabilistic attack trees are intended to address one of those sticking points. So there's a number of different scoring tools. I don't mean to get into quantitative assessment. We could do that for hours and hours. If anybody really wants, happy to do that. But of the scoring tools that we use, this is one that I typically prefer, called 4-factor. You can see that mission risk, just as per the DoD definition, is a combination of mission consequence and likelihood. We break down mission consequence into two pieces. The first is single system loss. What that means is, if this cyber attack is successful on this platform, how much of my mission will I lose? And we measure that in terms of mission loss, from 0 to 100%. Percent systems impacted is meant for that case. Again, I've spent most of my time in the aviation ecosystem, where you have a multiple set of platforms airborne. How many of them will be affected? So if I'm going to talk about F-16s a lot. I was an F-16 guy. I love my sleek and shiny single-engine fighter jets. So a lot of my examples will revolve around F-16s. So if you have 100 F-16s airborne, and I launch this cyber attack, is it going to hit one of them? Is it going to hit 10 of them? Is it going to hit all of them? And so that obviously dramatically changes the amount of mission loss. On the likelihood side, we break it into two pieces. Likelihood of attack success, which is the likelihood that this attack will be successful given that it's launched, and then likelihood of attack launch. As you can imagine, likelihood of attack launch is something you would love to get from your intel folks. And so ideally, that's where that will come from. I will tell you, any intel professionals in the room? Excellent. Are you going to be able to tell me that? Exactly. So don't go to the intel folks and expect them to give you a meaningful answer. The engineers and the programs and the operators are probably going to have to come up with their best guess. But ideally, it would come from intel. But what I'm really going to focus on is that one in the middle. And so how do we answer that question? What is the likelihood that a cyber attack will be successful? So again, we're looking for a combination of engineering, operations, and intelligence, because all of those impact that answer. Before I go there, you obviously know my answer to this question because I'm here talking about how to calculate likelihood. But it is true that there are many people that I talk to these days, many people that I greatly respect, that have come to the place where they think likelihood is just not worth the effort because it is just too hard. The uncertainties are too high, and we just don't know. So we're guessing. So just set likelihood to 100% and drive on. I empathize with that approach because I've spent a lot of time trying to calculate likelihood. And I've done a lot of work on the human assessment side where you end up getting radically different answers, and it's very frustrating. However, I think it's a mistake. And the reason I think it's a mistake to adopt that approach is that there are things that we can say with a great amount of certainty that our adversary will do. For example, exfiltrating information. I can say with great certainty that in case of war, an unfriendly country will try to exfiltrate information from us. I can say that with great certainty because they're doing it today before the war. And so I fully expect them to be doing it tomorrow. If you compare that to a cyber attack that, for example, again, this doesn't exist, I hope, but just making up a crazy example, if there were a cyber attack that would make every flying airliner suddenly crash, that would affect not just the combatants, but a bunch of neutrals, and might pull those neutrals into the conflict. So I think it is very reasonable to say that the probability of an adversary launching that type of attack is much, much less than of them exfiltrating information. So some things are clearly more likely than others. Some things we can test and we can say, we can show easily, oh, this is easy, I can do this. I've done this in the lab 12 times since Tuesday. Other things we can say, well, maybe if you had 4 consecutive miracle hacks and the planets were aligned just right, again, there's different likelihoods. There are times when we can say things are more or less likely. And the real problem behind assuming everything's 100% likelihood is that by definition, we will then misallocate our resources. Remember, what's this all about? This is all about making better decisions. And this is all about producing systems that are adequately survivable to accomplish their missions. And if we put the same amount of, if we assume everything will happen when it won't, then we're spending resources in a non-optimal way. Okay, so attack trees. Anybody, by the way, if you haven't figured this out already, you know, recovering fighter pilot, etc., please interrupt me. I'm happy to have discussions. They gave me extra time because somebody was scared off by the crowd. But so anyway, feel free to ask any questions. Has anybody heard of it? Some of you must have. I know there's a cyber-ish person in the back. Attack trees. Who's heard of them, used them before? Okay, they've been around a long time. Bruce Schneier, 1999, I think was the paper that's pretty famous about this. So the attack trees I'm going to show you are all upside down. So the root is at the top, and the leaves are at the bottom, and the branches are in the middle. And so basically at the top, you have what the thing is that the adversary is trying to do. We're going to be talking in terms of a notional unmanned aerial system that is called the Berserker. That some of you may have run into other places, but it... So in this particular attack, the adversary is trying to fly this UAS to an adversary-directed location. Maybe they want to fly it into a SAM ring and shoot it down. Maybe they want to fly it over the ocean. Maybe they want to put it where their forces aren't. Whatever they want to do, they're trying to make it go there. So there's at least 3 different ways that they could potentially do that. And then underneath that are all the ways that lead into those ways. And so you end up with, you can think of it almost as, it's a kind of a mix of an attack surface along with almost a fault tree as far as how you can produce that effect. Those nodes can all be connected in 2 ways. They can be OR. So for example, if up in the upper left, if an adversary wants to send a malicious navigation command, they can either gain control of the ground station or they can get into the middle of the ground station air vehicle link. Whereas they can be connected and. The only and on this particular one is where to send a spoofed navigation message on the 1553 bus, they have to both get a control of a device on the bus as well as successfully send a message from that device across the bus. Now, this is good. This is straightforward. And it's super simple to do the math if you start doing quantitative assessment. But what's the problem? The problem is coming up with those numbers at the bottom. And so that's the real issue. Nobody argues with the math. Nobody argues with the structure. It's where did those numbers come from? So I think step 1 is you start with any known data. Anybody heard of Douglas Hubbard? He's got some very angry books that are a lot of fun to read. The Failure of Risk Management is one of them. How to Measure Anything. If you're in the risk assessment, risk management world, you have to read The Failure of Risk Management just for entertainment because he is so angry. One of the things that he talks about, though, is that you have more data than you think, and you need less data than you think. And so let me show you an example of that. So these 3 values I can fill in with some historical data, even at the totally unclassified level. The reason is that 2 of them involve insiders and insider threats. We love talking about insider threats in cyber. And I can tell you that on some real assessments I've done, when I was working the assessment with the red teamers, they were coming up with values that I felt were unreasonable for insiders. And so I went out and I started looking for data. MITRE has some great studies, but those are not unclassified. But I was able to find this unclassified study. You can go Google it. That's what I did. It's by the Defense Personnel and Security Research Center that found there were 83 cases, confirmed cases of insider exfiltration of information between 1985 and 2017. So you can also then go and say, well, how many people were in the military and civilians in 1985, 1986, and you can back out a rate. And it turns out the rate is about 1 in a million annual. So every year, of any particular individual, there's about a 1 in a million probability that they will be convicted of exfiltrating information and giving it to a foreign power. So, of course, the next question is, well, obviously those are the spies that got caught, right? So what about the ones that weren't caught? So you can make an assumption. In this case, I went with what I thought was a pretty conservative assumption, and I assumed that we only catch 1 out of 10. Actually, I'll bet that if you were working at the classified level, I don't know this because I'm not a CIA guy, but I'll bet their data does exist on how many spies we catch versus how many spies are out there. There are ways to back that out. For one thing, we know how many spies we have, and we know how many of them they catch, and so there's probably a way to back out something other than a guess, but that's purely a guess. So that takes our rate to 1 in 100,000. Now, if I go back and I multiply out by a presumed number of people, again, just to reemphasize, this is a completely notional example, the number of people who would have access to that node, I put 200 for the ground station and 50 people for the encryption keys, then you get out of that, you get a rate. So you get a likelihood that could happen. And another place where I used what I called historical data or data is that in this particular case, this notional system is specifically designed to return to base if it cannot receive encrypted commands. And so I set the probability of it executing an unencrypted command to 0. Now we can talk about whether that's prudent or not. Should it be a small number, etc. Note that I'm talking about point values. When I get to the end, I'm going to tell you what I really want to do, which is use 90% confidence intervals to capture uncertainty. I'm breezing over all that right now to talk about the attack trees separate from that. But that's really the way that I handle that. Is I use 90% confidence intervals. Okay, so the next thing you can do if you don't have direct historical data is build simple models. So there is a large body of research going back to the 1950s that shows that simple models, even without weighting, outperform humans at nearly every probabilistic decision. It turns out humans are really bad at assessing probabilities. There's a lot of reasons for this. We have a lot of biases. We have a lot of heuristics. We have a lot of issues. We're not good at it. And so but you do need humans to figure out what factors matter. And you can pull out of the data, you can figure out the factors, and then you can build these very simple linear models, nothing cosmic from a math perspective. You can build them using historical data. You can build them using human assessment. This is the really fascinating thing. It turns out that if you build a model to answer a decision like a probability, given a set of factors, you actually get better performance out of the model built by the humans than by the humans themselves. So if you go to those same humans and you ask them the same questions, you will get less good results than the model. There's a couple of reasons for that. One is that the model abstracts out several biases that have significant effect upon human assessment. And it also gives you the opportunity to combine multiple humans into a single model. And I'll show you how we do that here on the next slide. Okay, so here's an example of a way that we did that in this particular notional example. So I built this atomic component model. And so basically a very simple model. And so the assumption is that an adversary is sitting on a controlled component with privileged access, and they are trying to get to a component under attack. And then they have one of 5 attacker goals: write malicious data, execute malicious programs, maliciously execute authorized programs, etc. If any of you recognize those are from JHU APL, that's from Hat Trick. I think that's a very good set of potential things that an adversary can do. And then the other thing we did is I had 2 other sets of factors, one for component cyber robustness, so how strongly designed is this against cyber attack, and then SSE process maturity. So how mature was the process under which it was designed? And so those were given all the possible combinations. That gives you 45 possible combinations for a survey that I can then send to my experts. The experts I wanted in this case were hands-on cyber testers. I wanted the guys with their fingers on the keyboards who were actually trying to hack into cyber physical systems. I will tell you my first model had 270 questions. That was not going to work. So you do have to aggressively reduce the number of factors as far down as you can. The way I did that in this case is I essentially abstracted out the connection, because as we figured out, the connection didn't really matter. Because if you've got privileged access, then you can use whatever communication medium are available to you. So with that data, then I can survey them, and then I can build a model. This is just Excel. This is nothing cosmic. And so you just dump it into Excel. You can run a multiple linear regression, and you can back out of that essentially what the coefficients are for each of those potential factors. And so then I've got a simple model, and I can plug in for any set of factors. It will output a likelihood. Along the way, even Excel will give you some interesting first blush type of statistical measures, things like R squared, significance, etc. Interestingly, all of these that I've run have done very well from a statistical perspective, better than I often felt that they should. So the statistics are strong. It doesn't necessarily mean they give the right answers. Of course, any statisticians in the room will understand that. In this particular case, we ended up with 0.3 for the one node where that applied. And so that was, we assumed that they were trying to write malicious data with an average component cyber robustness and compliance-focused SSE process maturity. Okay, and then the rest, we did the human assessment. And so this is actually, I went ahead and plugged these in, again, using not a lot of deep thought, just for purposes of the example. And so, although I will say, so what do we typically do with this? What we would typically do is we would put a bunch of subject matter experts in a room, and we would ask them the question at the top. We would say, what is the probability that an adversary will be able to fly this system to a point of their choosing? And they will all come up with answers. The problem with that is it's too abstract and too high up. So I think we actually gain, even if all you're doing is asking the humans, this structure forces them to answer much more specific questions. So it is a much more specific question to say, what is the probability that an adversary will be able to launch a cyber attack over SIPR that will compromise control of the ground station, than to say, what is the probability that an adversary will accomplish this giant mission effect? And so you can start talking about things like what data you have, what tests you've done. Actually, I'm getting ahead of myself on the next slides. But remember, of course, all the normal issues with using SME assessments apply. There are calibration issues. Humans tend to be quite a bit overconfident in our capabilities. And so if you ask someone who is untrained for a 90% confidence interval, they will only be right about 50% of the time. So that means they're about 40%, and that's across thousands and thousands of data points. So we typically think we know more than we do. But the good news is that can be trained out. So there's a set of process. About 85% of people can become fully calibrated, where when they give a 90% confidence interval, they are approximately 90%. They're right 90% of the time, which is what you're hoping for. I will say, having gone through that training several times myself, at the end of the day, you finally realize you're dumber than you think, and you start multiplying all your estimates by 2 or 3 to make them big enough to capture the actual amount of uncertainty you should have. Yeah. All right. So then you can do the math. As I said, the math is easy, uncontroversial. Nobody argues with the math. And any simple, Excel can easily handle it, etc. But so we've got all these things. The next thing you can do is start looking for opportunities to improve your overall attack tree. So I went and I started looking at the places where we did subject matter expert or human assessment. Said, well, do we have any data here? I'll bet we do. If this were a real system, I have no doubt, especially at the classified level, somebody's got some data on MIL GPS spoofing, how easy it is to do, what the probabilities are, other types of nav sensors. I know there's data out there on adversary or on 1553 buses and other devices, and the probabilities that we've seen for various types of supply chain attacks. So we've got data on most of these things if you're a real system. You can also start building models. So if we don't have enough data, you can start building some of those simple models, even if you're using human input into it. And of course, we're all testers, or many of us are, so you can test. So if you want to know what's the probability that they're going to be able to launch a traditional IT cyber attack, go do an adversarial assessment, and let's find out, and let's see what that looks like. And of course, focus on testing key nodes. We're going to get back to this in a minute, but one of the real power, the value to this is, I'll show you when you do a sensitivity analysis, you'll see there's really some things that are worth testing, and there's probably some things that aren't. And there's some things that we really shouldn't care that much about when it comes to mitigation. So here's the sensitivity analysis. In the aviation world right now, we love to talk about 1553 buses. And I talk about them a lot too. And bus defenders and there's a whole bunch of companies making them, and the DoD is spending millions and millions and millions of dollars on defending the 1553 bus. Again, completely made up notional example, but in this case, your sensitivity there is 1.68%. Compare that to your SIPR traditional cyber IT attack. You can see as you look at the probabilities as they work their way up the tree that most of your risk is actually through a SIPR attack into your ground station. So if you're going to spend some mitigation money, you probably ought to look at spending it here. I mean, the 1553 bus defender is cool, but that's probably not where you should focus. And so if you build these type of attack trees out, you can start to see where you can start putting your money, even if you ignored all the numbers. And the other thing I haven't talked about yet, it's normally part of my pitch in other type of briefings, is what is this number? You know, when you get to the top. And I guess I'll talk about that in the real example. Before I get there, I did mention uncertainty. That's one of the big things that I tend to jump up on soapboxes and get excited about. And so because of the importance of tracking uncertainty, my preference is to use these 90% confidence intervals. So this is an example of the same attack tree done with 90% confidence intervals, which means that you are 90% confident that the correct answer is in between those two values. The math is slightly harder, but it's not bad. You can do it in Excel if you're patient. And if you're not patient and you've got access to something like R will spin this out very, very quickly. It's very simple, very easy to do. Okay, so overall, advantages to this approach. One thing is that it forces focus on the mission. Because remember, the thing at the top is a mission effect. Like was talked about previously, we can get wrapped around the axle on vulnerabilities that don't lead to mission effects. So this puts the mission effect front and center. It provides specific, falsifiable, and testable predictions at all levels of the attack tree. It improves consistency and repeatability, especially with the models. With data will always give you the same data will give you the same answer, and models will always give you the same answer, even if they were built off of human assessors. If you give them the same inputs, they'll give you the same outputs every time. This does provide the ability to calculate return on investment for various mitigations. So you can look at your attack tree, and you can say, okay, if I do this thing, then I've got the ability to, then here's how it changes, and therefore my overall risk changes this much. I can compare that to this other thing that I might do, and I can figure out what I would prefer to do. I will say from a practical perspective, from somebody who's done a bunch of these type of risk assessments in the past, this also largely gets you out from going to the program engineers and trying to get them to give you all the probabilities. They really hate that. And it takes a lot of training, and it takes a lot of patience, and you usually don't get enough time with them. This lets you kind of avoid that. Some disadvantages, obviously this could be seen as more complex than the traditional 1 to 5 risk matrix scoring. I didn't go into that. If anybody wants to defend risk matrices, happy to have that conversation. There's a lot of reasons why those are not always helpful in driving to better decisions. A couple of the biggest ones, one is that if you look at a 1 to 5 risk matrix, you might intuitively think that you're looking at 5 different scores. Really, you're not. You're looking at almost a binary score, because 75% of the scores are 3s or 4s historically, if you go back and you look at the numbers. And so really, it's a 3 or it's a 4. That's it. And so it's almost a binary scale. And why that matters is if you make what appears to be a small change, like your risk goes from 4 to 3, it will take it potentially from the top of your risk stack to the bottom. And so it's a very non-discriminate scale. It's got issues with reversing scores in different nodes and areas and all kinds of stuff. There's all sorts of academic papers. It's been well studied in the literature. Medium does feel more comfortable than 40% probability, mostly because it obscures our lack of uncertainty. Whereas when we talk in terms of actual probabilities, we're kind of forced to face our level of uncertainty and explicate it. And in some cases, you may have to go to a program office or program manager and say, our best guess is it's somewhere between 10 and 90%. And that's not very satisfying, but that may be reality. And what that if it's important, then that probably means we're going to need to do something else. We're going to need to do some testing. We're going to need to do some research, analysis, etc. And there is a little bit of computational complexity when you go to confidence intervals instead of point values, but it's trivial on any modern system. A government laptop can run an Excel file that will do those 90% confidence intervals in the Monte Carlos. Okay, so MBSE. Trying to remember what version this was. I was told to keep this super short before they told me to not keep it so short. Unfortunately, I didn't put in any of the slides that showed where we're actually doing this. And so what we've done is we've taken this example, and it's this MQ-99 Berserker, and we've built out a complete set of attack trees within an MBSE environment. The reason why that's important is that these quickly get out of hand. So on this conceptual level UAS, there's about 350 nodes in all of the attack trees. And so if you're trying to track that in PowerPoint, good luck. But within an MBSE environment, it becomes much more doable because it's tied to the actual structural, architectural, and mission models that you have in the system. But most importantly, there's a lot of repeatability. Like, for example, there were a lot of attacks that came through the ground station or the maintenance system, or, and so there were portions of the attack trees that we were able to copy paste essentially, and then combine them all up to, essentially we came up with 8 high-level risks and then a final top EML or expected mission loss, which is typically how we like to measure risk to mission systems. And that's basically the likelihood of bad multiplied by how bad it is if it happens. And so if I tell you you've got and I'll talk about, I don't have that on here either, do I? I stripped out all kinds of stuff. So another thing we did is we took all that information and we took it into AFSIM. And so the point was, how can we use modeling and simulation? And so we built a cyber attack on the MQ-99. We built out the MQ-99 Berserker and a DOT&E tool that is GOTS, that is freely available, called COLE, Cyber Operational Lethality and Effectiveness Tool. And so that gave us our 90% confidence intervals, which we then input into AFSIM as a mission effect. The particular cyber attack was a supply chain cyber attack against the radar warning system. And then there was an AFSIM scenario with 2 berserkers flying into threat rings, 2 additional berserkers all being controlled by an F-35, trying to drop small diameter bombs to destroy some targets. And essentially, we ran it 50 times. We figured out, okay, how often do these berserkers destroy their targets and how often are they shot down? And then we input the cyber attack, which again was only a probability. So sometimes the cyber attack was successful and sometimes it wasn't. And then we got to see what those effects were. How often were the berserkers shot down and how many targets did they destroy? And at the end of the day, if you put 50% weight on both, it ended up to be about 35% mission loss due to that particular cyber attack. Again, ignore the numbers, it's all made up, but the point was that's a methodology that gets you to a meaningful answer when the warfighter says, well, yeah, why do I care? What does this mean to me? Well, it means that you are 30% less likely to destroy your targets if this cyber attack is executed. So that's something that's much more meaningful that they can work with. Okay, and I think we talked about all that. And I think we have a few extra... Oh, before I go there, any questions? Yes, please.
What does MBSE stand for?
Oh, that's fine. Model-based systems engineering. And so that's basically trying to convert all the paper into a bunch of models and files that all talk to each other, and it's going to solve all of our problems. It hasn't quite yet, but next week. Yes, sir.
Maybe you're doing a policing mission off the coast of Iran,
Yeah, and you're absolutely right. In fact, I would argue it's much worse than that. In that, so you have to be very specific. If you're going to measure this, you have to measure it in an environment. It's like saying you're in the lab. You have to know the temperature of the room to calculate, the precipitate of a reaction. It's the same sort of thing. So you have to assume all of those things. And so you have to be very clear what those assumptions are. And I didn't talk about that at all, but that's part of kind of the larger URAMS process, is tracking all of those assumptions. And then, like the AFSIM scenarios, one of the things we figured out doing that is those scenarios really matter. I would not want to make any specific decisions based off of just a single or a handful of scenarios. Ideally, what you really need to do is get up to the campaign level. And so you need to feed all that information into a campaign level simulation, and that's really where you should be getting your results out of. Saw some interesting things in some of the earlier AFSIM scenarios that we ran. Depending on where you put the surface-to-air missiles, you get very different results. In fact, in the first set of things we ran, I thought this was fascinating. We ran it at that time. We ran it 100 times, and then we ran it 100 times with the cyber attack, and the cyber attack increased slightly the probability of the berserker hitting its targets. And we had to go back and look at that and go, okay, well, that's interesting. What happened? Well, what was happening was that they were driving straight and level before dropping their SDBs, and if their radar warning receiver worked, shortly before weapon release, they would get lit up by the SAMs, and then they would dodge. If the radar warning receivers were dead or were not functioning because of a cyber attack, they just continue driving straight forward, fat, dumb, and happy, drop their bombs, and so they had a higher probability of success on dropping their bombs. So that's just a simple anecdotal example of why a single scenario is not good enough. And so you need to run a range of scenarios and then roll them up to the campaign level, which, by the way, forces you as a program to say what war you're designing this thing for. And of course, any program will say, well, I'm designing it for all the warfighters. Well, somebody is the winner. I think we know who the winner is today, if that question gets asked. And I think we all know what scenario we ought to be running. And that's what we should be basing our decisions off of. Did I answer your question? Sort of. And then I started jumping on a soapbox. Any other questions? Ma'am.
I had more of a comment. Thanks. Yeah, back on slide 20, when you were listing the advantages and disadvantages. And so I'm seeing this more from typically how I'm doing operational testing. I'm thinking less about the likelihood of attacks and more thinking about like the value of any particular element of data or loss of functionality, and what does that mean for the mission. So when I looked at this list and was looking at your disadvantages, I thought that your second point there really is an advantage to this approach, because even if I'm not thinking about likelihood as much, this at least gets me familiar with, where are those exposures in my system and what information is valuable to me. And so I see any opportunity to go through an exercise like that and identify in more detail where information or functionality could be lost, that is helpful in that case. So I see that as an advantage. That's my comment.
Yeah, and honestly, as part of my normal pitch, I skipped over it for whatever random reason. I actually say that. And that, yes, it's a disadvantage from the expectations of a program in that it's a lot of additional work, but it's work you should do anyway. And it gives you also, and the other thing I didn't talk about, really part of this process, and another reason why we went down this road, is that there are other NBCRAs out there. There are a number of them that are much more commonly used than the one that I'm most used to using. And one of the issues is they tend to be too large and too hard to execute, because one of the steps is essentially figure out your attack surface. And they have different names for how they do that. But you're trying to determine the entire attack surface. What an attack tree lets you do is just figure out the attack surface you care about. Instead of trying to do the entire system's attack surface, it gives you the attack surface that can lead to, again, there are other pieces of this. We typically use STP-ASEC, and so we talk in terms of unacceptable losses. It gives you only the attack surface that can lead to your unacceptable losses. And so that brings it down to a manageable size that you can actually execute.
So we do have one question on Zoom. Armand asks, shouldn't you be using multiple testing corrections, Bonferroni, 2K, etc., if you are using more than one confidence interval? Additionally, confidence intervals don't talk about probability, they talk about likelihoods. Would a Bayesian approach be better suited here?
So I would consider myself a Bayesian. I'm a fan of that approach in general. In this particular case, we went with the simplest, most straightforward approach that we could. I would not be opposed to some of those other methods, but I'll just say that we went caveman. And this is DataWorks, right? Most rooms I brief this in, all the eyes roll into the back of the head and they go, way too many numbers. Oh, wait, my head's exploding. So in this room, I'll get asked that question. In most other rooms, I get, this is way too complicated. So we were trying to find a balance there. And so I don't disagree with the comment, and I don't disagree that those would potentially be better approaches, but we were trying to keep it as simple as possible. All right, ma'am. Mm-hmm.
So, like, if the start or like in a peacetime situation, I totally agree about the exposed situation. But isn't it true that likelihood is completely fluid and will ever change because you will get to a point maybe in the conflict that it is a break-glass situation, and then the more likely scenario would be that all the planes would drop out of the sky.
So I guess my response to that would be, I was trying to come up with almost a silly level example in that, yes, context definitely matters, and there would be potentially circumstances. The specific example, I may not have explained it well, was not just that they knock all of your airplanes out of the sky, but they knock every airplane out of the sky to include all the airplanes of neutral countries that are not in the war, that they may have just pulled into the war. I was trying to use that as an example of something that they might choose not to do because it has significant negative impacts on them. By the way, I am unaware of any cyber attack that would jettison the left wing of every flying airplane. Just mention that in passing for those of you getting on an airliner later. But yeah, so I mean, that's a good point. And I think it comes back to, you've got to determine what question you're trying to answer. And we tend to want to answer all questions at the same time, and that's not feasible. We have to pick a question. We have to pick a campaign. We have to pick a scenario, and then say, we're going to design around that. And so whatever that is, if that's the initial stage of a large-scale combat with a large, unfriendly country, or whether it's, it used to be the global war on terror, or whether it's the Fulda Gap, if you go back far enough, whatever that is, I think you could, I would just be ecstatic if I could get people to start thinking this way, let alone running this on systems. Over time, you could, in theory, do multiple versions of it. You could do, a European scenario, and you could do a Pacific scenario, and you could compare different mitigations and how they played out. I mean, you could do all that, and I certainly wouldn't be opposed. But I think it'll be a huge lift to even get people to run the first scenario. That's why I generally talk in terms of pick one, and that's the one that you design towards. All right. Anything else? Okay, so we have a few extra minutes. Feel free to walk out if you don't care about AI. Many people are interested in AI. It's the latest cool buzzword. And we did, as part of the research I just showed you, we did do kind of an AI spiral as well. And the question was, what could we do using generally trained large language models, which is what we had access to answer these problems. So specifically, we looked at ChatGPT 4.0 and Llama 3.3, and the bottom line is the results were interesting, and there were ways that we could structure the questions that would get us to about 80% accuracy of what if I used my human cyber assessors as the baseline. So if I use my human cyber testers as the baseline in building the model, so this is all about building that model that I showed you a while back, how well could these large language models do that? However, I will say that most of the time, the results I got out of the model when analyzed were indistinguishable from random. So I also put a bunch of random numbers in and looked at the statistics around both of them. So most of the time it was garbage. It wasn't always clear it was garbage, but most of the time it was. But there were times when it appeared to be doing something interesting. So this is kind of just all the trials. Again, hundreds of runs. In general, the only way to be successful was to run the runs individual or very small sets. If you tried to ask it too many questions, it ran out of tokens and it would just start generating random numbers. And so of course, it doesn't tell you it's doing that. So it did require a lot of caution. So here's a whole bunch of different runs. They're on the left. The testers are at the top. And so the correlation coefficient with the testers, of course, is 1.0 because that was their answers. A different human SME, which actually was me. I'm not a hands-on cyber tester, but I'm familiar with a lot of cyber things. So my correlation coefficient to their answers was about 0.83. And you can see most of the time it was essentially indistinguishable from random, except for the runs down there at the bottom. And those are the only ones where the correlation coefficient was, again, about 80%. This is interesting if you have the right answer, but how would you know which runs were garbage and which weren't if you didn't have the right answer? But it turns out the other thing you could do is look at the 90% confidence interval width. So for all the ones that were garbage, it was over 90%. And the ones that worked, it was about 50%. So significant difference there. So one potential way to cross-check whether your LLM is spitting out complete garbage or not. So that was interesting. I'll pass over this. This is all the coefficients put together into a chart. The couple other interesting things that I just thought were fascinating. One is that this is hundreds and hundreds of trials. Once and only once, it gave me answers over 100%. And so I asked it. It's an LLM. I said, well, how could these answers be over 100%? And it came back and it said, oh, I'm sorry. That was due to the way I was combining the factors. Let me fix that for you. And it spit out the results again, and it truncated all the numbers that were over 1 down to 1. I don't know why. Again, I'm mostly mentioning this to increase everyone's caution about using these tools. The other fascinating thing, again, I only saw this once out of hundreds of runs. It went on strike once. So if you look at this on the right, it was spitting out fairly normal numbers down to about, whatever that was, number 9, and then it went on strike, and it gave 0.5 all the way down for all the rest of the results. Didn't say anything, didn't complain, didn't say I'm going to report to the union office. I don't know, but that was fascinating to me, which just highlights you really can't trust these things. They can be tremendously powerful, but they will do all kinds of weird stuff if you're not looking. here's another interesting thing. So I went and I asked it I asked it the same questions that I asked myself as a human assessor. And there are a couple of differences that I thought were interesting. One is that the internet, from ChatGPT anyway, is convinced that Nipper is essentially unhackable. Inconceivable that an adversary, or Sipper, sorry, excuse me, that inconceivable that an adversary could get onto Sipper. So it gave very low values. It thought it was utterly inconceivable that anyone could break AES 256-bit encryption. It insisted that there was a zero probability of that happening. Of course, ignoring side channels and implementation errors and all the things that we all know about. And it also, so I thought those were pretty interesting as well. So am I using AI for any assessments? Probably not right now. I think that we could do better. I think that we can train potentially AIs with a better data set, but unfortunately, if I had that data set, I would probably use it as historical data anyway, because it's really hard to come by any decent set of data in this area. So sorry, that was a bonus because they gave me extra time. Any questions on that or on any of the other material? Yes, sir. Yes, I was very careful about scripting it, and it was copy paste from my script every time to make sure that they were all the same. And it almost seemed to depend on the time of day. Like those 3 runs that worked were all in the same time frame. When I tried similar runs in other times, I got different results. So again, ChatGPT in particular is cloud-based, and so it may be dependent upon the load on the servers, or I don't know. Again, my primary takeaway from all this is, wow, this stuff is really interesting, but I certainly wouldn't trust it today, and I would be very careful with it. Yes, sir.
Sort of with the GPT prompts, were you like clearing your cache within ChatGPT, or did it understand the memory that you had?
Yeah, no, I was actually explicitly trying to avoid memory and basically restarting it. So, yep. Alrighty. Well, thank you.
Oh, I did have one question. So you had discussed, kind of the comparison between aircraft survivability from a kinetic perspective. And of course, we have, 80 some odd years of data about aircraft survivability from, global conflicts, and comparing and contrasting that for probability of hit. How much more data, do we need for the ability to do this for cyber to feel more confident about some of the results that we're getting?
I don't know that I have a good answer. I struggle because the data we do have is very siloed, because part of it is classification. So things go to very high classifications very quickly. They become compartmentalized, and cyber experts in program A don't know what program B found and can't know based upon the compartmentalization. I also struggle. I'm not a data expert, but I think there's huge issues in coding and in categorizing the data. So even if we had a giant data set of every cyber attack into an airplane, which honestly, that would be a really small set, at least from what I've seen. How much of it would we need? Almost any of it would be better than none of it, which is what we have today. So I would take any data, but it comes down to confidence. Like if you were asking for 99% confidence, then yeah, it's going to take a lot of data. If you're looking for a reasonable first guess to inform better decisions, then a small amount of data may be sufficient.
Any other questions? Oh, and looks like we have one on Zoom. I guess this is kind of more of just a comment for everybody. Let's see. So Kirsten asks, so the only validation of a battle sim I found, and then she cites this article, is there a danger in presenting detailed quantitative results to decision makers without any model validation? From years working on missile sims, I decided that uncovering bugs or potential vulnerabilities was more useful than predictions without enough validation data.
So, absolutely, and I didn't discuss it, but before you really spent a lot of money, what you really use this for is informing your test planning, and then you go fly it. And so, really, you do need to get to that point. You need to validate your simulations. And again, it almost turns into a philosophical discussion of what is the most useful way to make better decisions. I think these can help decision makers conceptualize and make better decisions. Other people disagree. I think it's an open discussion. What's the best way to better decisions? All right. Well, we're after 3, so thank you.